Right on. Geometrical isomerism in polyene. So what are the polyenes? More than one double bond, right? So in previous class we have studied dienes, right? If there is a carbon-carbon double bonds, like 2 or more double bonds are present, tell me what is a cis, which is a cis and trans? First molecule, identical groups are opposite side, first one is a trans, and here identical groups are same side of the double bond, it is cis. Okay, then like that, even if there are 3 or more double bonds are there, it is 2 double bond. If there are 3 double bonds, take that also example. If there are hydrogen, methyl, hydrogen, methyl, hydrogen, here hydrogen, here is methyl, hydrogen. So it can also exhibit geometrical isomerism. Identical groups are same side, it is cis. Here identical groups are, tell me, it is a hydrogen, here is, take hydrogen here, this is trans, now here HH, cis, so that you can identify the cis and trans. But now question is, it can have how many total number of geometrical isomers? Then how do you calculate? That is calculation of geometrical isomerism in polyenes. Okay, right on. Calculation of geometrical isomerism in polyenes. Calculation of geometrical isomerism. Geometrical isomerism in polyene. So take case 1. Case 1. If polyene, write down, if polyene contain different groups on terminal, different groups, if polyene contain different group on terminal double bonded carbon, okay. So what is the meaning of this? If the polyene contain different groups on terminal double bonded carbon atom, then how do you calculate the number of geometrical isomer? Their formula is number of geometrical isomers equal to 2 to the power n, where n is equals to number of pi bonds. Let us take example. CH3, CH double bond, CH double bond, CH. Let us take double bond CH. It is ET. Now tell me, it is a polyene contain 2 different group on terminal double bond. Say this is a double bond, terminal double bond carbon. If the terminal double bonded carbon attached to different groups, it is a methyl, it is ethyl. So if the terminal double bonded carbon atom attached to 2 different groups, then the number of geometrical isomers equal to 2 to the power n, where n equal to number of pi bonds. How many pi bonds? 1, 2, 3. Therefore, it is 2 power 3. It is. So therefore, there are 8 geometrical isomers are possible for this molecule. But the condition is terminal double bonded carbon atom should be attached to different group. Okay, next, case 2. If terminal double bonded carbon atom attached to same group, right? So if the terminal double bonded carbon atom attached to same group, again there are again two condition A and B. A, if molecule has even number of double bond, there is one formula. If molecule has odd number of double bond, there is another formula. So therefore, if molecule has even number of double bonds, then number of geometrical isomers is equals to it is a 2 to the power n minus 1 plus 2 to the power n minus 2 by 2. It is when there is a even number of double bonds. Okay, where n equal to what? Number of pi bonds. Next, B. If molecule has odd number of double bond, then number of geometrical isomers equal to it is a 2 to the power n minus 1 plus 2 to the power n minus 1 by 2. Okay, for example, take one question. Calculate the number of geometrical isomers in the following. Calculate the number of geometrical isomers in the following. 1, 2, okay. So just calculate number of geometrical isomers for the following polyenes. Tell me, here first you need to identify terminal double bonded carbon, whether attached to same group or different group. Same group. If the terminal double bonded carbon attached to same group, again there are two conditions. There is a even number double bond or odd number of double bond. So therefore molecule has how many double bond? 2, even number. If there is a even number of double bond, the number of geometrical isomer equal to 2 to the power n minus 1 plus 2 to the power n minus 2 by 2. where n equal to number of double bonds. Substitute the double bond, that is 1 2, here 2, 2 minus 1, 1, 2 plus, this is 2 minus 2 by 2, 0. Therefore how many? Total 3, no. So 2 plus 1, that is 3. Next, here it is double bonded carbon atom, terminal double bonded carbon atom attached to two different groups. If there are different groups, then the geometrical isomer equal to 2 to the power n. Then it is a 2 to the power 2, 2 power 2, 4. Next here, now this is a double bond carbon, terminal double bond carbon. So terminal double bond carbon is methyl, this is ethyl. Two different. If it is a different 1, 2, 3, 4, so it is a 2 to the power 4, 16 geometrical isomers. Next here, it is terminal carbon atoms are attached to same group. Then if it is the same group, then identify the number of double bonds, 1, 2, 3, 4. It means a even number of double bond. For even number of double bond, formula is given, substitute in the formula, you will get answer. Okay, so this is the geometrical isomerism in polyenes. Okay, next last one is, what is last one? Geometrical isomerism in cumene, no. Right, yes or no? Cumene. Now so far what we have studied? Where we have studied geometrical isomerism? 1, tell me. Geometrical isomerism in alkene. 2, oximes, that is aldexamide, ketoxime, alkene having double bond. Then here is C double bond N. Next is diazo compounds, N double bond N. Next is cycloalkanes, like cyclic compound. Next is, so in conjugated, not cumulated, so conjugated diene and polyene. Okay, so geometrical isomerism in conjugated dienes and polyenes. Better write polyenes only, diene, polyene, all. Okay, next sixth one is geometrical isomerism in cumulated alkenes, that is called cumene. Okay, right, next slide. Geometrical isomerism in cumenes. Geometrical isomerism in cumene. Tell me. So what is a cumene and what is the structure of cumene? Tell me, what is the cumene? Right, cumene is, right, in alkene, if long chain carbon atom containing all double bonds, right, isn't it? If double bond present in all carbon atoms like this, they are what? Cumenes. Right on. Cumene. Right, if double bond present, continuous position of long chain, if double bond present, continuous position of long chain carbon called cumene. If double bond present, continuous position of the long chain carbon atom called cumenes. Okay, next, right. Right, see cumene, listen here, cumene can exhibit geometrical isomerism. Again there is a condition. Condition is cumenes containing even number double bond like 1, 2, 3, 4, even number double bond, they do not exhibit geometrical isomerism. Cumene containing odd number of double bonds, right, it can exhibit 1, 2, 3. Therefore here a cumene with even number of double bonds do not exhibit geometrical isomerism, but a cumene with odd number of double bond can exhibit geometrical isomerism. Then what is the reason? So listen first, a cumene with even number double bond, even number of carbon-carbon double bond, it do not exhibit geometrical isomerism. This is because if there is a even number of carbon atom, like for example, let us take this one. If there is a even number of carbon atom, then this terminal carbon atom hydrogen, they present in different plane. If it is a hydrogen or alkyl groups, let us take methyl, it is a hydrogen, and this terminal carbon comes, it is one is a methyl, here is hydrogen, it is in different plane. It means if the cumene containing even number of double bonds, then the terminal carbon atoms groups comes in opposite planes, not in same plane. But what is the condition for the geometrical isomerism? There is a condition for geometrical isomerism is carbon-carbon double bond and all the atom should be in same plane. Even though we have not written this condition, but it comes no. Why? It is sp2, it is also sp2. If the carbon atom sp2, it is a plane, it is also plane. That's what all the atom A, B, C, D should be present in the same plane. Therefore this is also one condition for geometrical isomerism. But here due to two double bonds here, continuous position and even number of double bond, so here methyl hydrogen, it is like away from the observer and it is towards observer. It should be like this. If I take a pen here, now suppose here methyl like this. If it is like this, two groups are like this on this carbon it comes like this. Okay, it is one here, one more here, like this. It means it comes in different plane. Actually it's supposed to be like this. If it is here, it should be like this only. If it is like this, they can form geometrical isomerism, but it comes opposite plane. That means if the cumene containing even number of double bond, the terminal carbon atom groups comes in different plane. Whereas if the cumene containing odd number of double bond, 1, 2, 3, okay, if there is a odd number of double bond, then terminal carbon groups comes in same plane. Why this is? We need to understand this, how and why. So therefore, to understand this, we need to understand the orbital diagram. Okay, so let us take carbon-carbon double bond, two double bonds. I'll take here 1, okay, there are two groups here. Can you tell me this carbon undergo which hybridization? sp2. If this carbon undergo sp2, it form how many sp2? It form 3 sp2. 1, okay, 2, it is 3 sp2. Okay, if it is undergo sp2, then each carbon also has one unhybrid, what? One unhybrid p orbital, no? So that is, I'll write here unhybrid p orbital. I'll take this is a px, unhybrid p orbital. Next, this is carbon 1, it is sp2. This is carbon 2, it is what? sp. If this middle carbon undergo sp hybridization, it form how many sp? 2 sp, no? Okay, this is 1 sp, it is another sp, right? Therefore it is sp, right? If carbon atom undergo sp hybridization, it form how many unhybrid p orbital? It has 2 unhybrid p orbital. Okay, so those 2 unhybrid p orbital, they are perpendicular, no? How they are? If it is a px, it is like this, px. Where is Py? Py is a perpendicular to Px, like this. So therefore, now let us take this is a Px. Okay, the red color orbital is Py. Okay. Next, there is another carbon. Another carbon is what? sp2. If another carbon undergo sp2 hybridization, it forms how many sp2? 3 sp2. One sp2 forms overlapping. Which overlapping? It is a sp2 overlapping. This overlapping it is a sp2 sp overlapping. Okay. Now there is another 2 sp2. 1, 2. Both are sp2. Now if it is undergo sp2, it has one unhybrid, that is, which is px. Okay, now tell me what is the overlapping now. So this px overlap with px, right? Px overlapping, you'll get one pi bond. Next, tell me, it is a py. Therefore it is a py, that means when carbon undergo sp2, it should have one unhybrid p orbital. That unhybrid p orbital is, it may be px, it may be py. Here we should take py. There should be one, no? You can take px or py. Here py comes. Why? If there is a py, then only this py can overlap. Otherwise this bond is not formed. That's what this py overlap with py. Now tell me, now here px overlap. Okay, here py. Now what is the px py? Both are perpendicular. That's what, if the px forms in one direction, it goes in opposite plane. Therefore here there is a bond is like, for example, like one hydrogen is there, one something methyl is there. Okay, it is hydrogen, here is something methyl group is there. Okay, so it is in on the plane. Suppose if you take on the plane, it goes out of the plane. Why? You see it is a py, no? Pi bond is formed by overlapping of py. This py overlapping is always perpendicular to px. That's what, if the px on the plane, it comes out of the plane. That's what you will get like this. So here, if it is a hydrogen here, it is a methyl here, this hydrogen and methyl comes out of the plane because of this overlapping. That's what, if the molecule having cumene having even number of double bond, so then the groups present on terminal carbon atoms goes out of the plane, means they are not in same plane. If it is on the plane, that is out of the plane. That is on the plane, it is out of the plane because of this overlapping. Here px overlapping, it is on the same plane, like one plane. It is a py overlapping. This is py overlapping, perpendicular to the px. That's what the group present on the terminal carbon atom are in different plane. Therefore they do not exhibit geometrical isomerism. In fact, they do not exhibit geometrical, they exhibit optical isomerism. We will study in optical isomerism. So therefore, if there is a even carbon atoms, they do not geometrical but optical. For optical condition, this is a condition, no? For optical isomerism, they should not be in same plane. That was the condition that we will study separately. Therefore, it exhibit optical but not geometrical. Next, if you take, it is a odd number of carbon atom. Tell me, let us take this one. If it is a odd number of carbon atom, let us take here only carbon double bond 3. Okay, there are groups here. Now tell me, this is what? sp2. It is sp. It is sp. It is sp2. Okay, now let us take first carbon. First carbon is what? sp2. 1, 2, 3. sp2. Second carbon is sp. sp means how many? 2. 1, 2. If it is sp2, how many unhybrid p orbital? 1. Okay, it may be px or it may be py. Now if it is sp, it is 2. One is a px, another is a py. Next, px overlap, no? Okay, next, third carbon is again sp. This is undergo what? sp, then 2 sp. If it is a 2 sp, how many unhybrid p orbital? 2, 1, 2. Again one is a px, another is a py. Okay, now let me take it is a py p overlapping. No, I'll take this is a py, this is px. Tell me, these two overlap now. Next is what? sp2. sp2, how many sp2? 3 sp2. Okay, how many unhybrid p orbital? 1. Okay, it is a px. No, it should be px only. px. Now tell me here. Now this bond is formed by px. Now this bond is formed by px. It means these orbitals lies on the x-axis. Okay, this bond also formed by px. Therefore these orbital also lies on the same plane. That's what you will get like this. Hence it exhibits geometrical isomerism. For geometrical isomerism, this is a condition. All the atoms should be lies on the same plane. If it is different plane, it will become optical isomerism. Therefore, so this is can exhibit geometrical, this cannot. Py. Which one? Let it be py perpendicular. We want atoms. You see the which atoms are again? This is one atom, two atom. They are x-axis. It is two atoms x-axis. All the atoms should be in same plane. Right? It comes in same plane. That's what it can exhibit geometrical. This cannot exhibit geometrical isomerism. Okay, fine. Next is, if it exhibit geometrical isomerism, then how to identify? That question is, first write this. Geometrical isomerism in Q mean written now. Have written what are the Q means, right? So next write case 1, right? Case 1, Q mean with even number of double bond. A Q mean with even number of double bond cannot exhibit geometrical isomerism. A Q mean with even number of double bond cannot exhibit geometrical isomerism because terminal carbon atom groups are present. Which plane? Same or different plane? Different plane. Present in different plane. Okay, then take this structure and this. Okay. Okay, next, case 2. Case 2. Right, a cumin with odd number of pi bonds, a cumin with odd number of pi bonds and terminal carbon atom attached to different groups, two different groups, and terminal carbon atom attached to two different groups can exhibit geometrical isomerism, because the groups on terminal carbon atoms present same plane, different plane, same plane, present same plane. Okay, so this is like, see here, a condition is there should be a odd number of double bond, 1 2 3, and not only that condition, there should be a odd number of double bond and terminal carbon atom should be attached to two different group, like H methyl and methyl H. It should be two different, AB or ABCD. That is a common condition, no? So therefore there should be a odd number of double bond and two terminal carbon should be attached to two different group. Okay, take this and this also, like AB, it is CD, and take this. Okay, so write in question, which of the following do not exhibit geometrical isomerism? Which of the following do not exhibit geometrical isomerism? So which do not exhibit geometrical isomerism? Why? So first one is not. Why it is not? It is a symmetrical ketoxime. No, it actually ketoxime. This ketoxime has symmetrical structure, right? So this group is same. No, therefore symmetrical ketoxime do not exhibit geometrical isomerism. Next, this 1, 2, 3. It is a cumene. A cumene with even number double bond do not exhibit, but odd number of double bond can exhibit. So, but here is CH2, CH2. So, terminal carbon atom must be attached to two different groups. Therefore, it do not exhibit geometrical isomerism. Next, what about this? Terminal carbon atom attached to different group, methyl hydrogen, all right, but there are two double bonds. A cumene with two double bonds do not exhibit, that is even number double bond do not exhibit. And here 1, 2, 3, 4, it also even number double bond do not exhibit. But see, remember, with even number double bond can exhibit what? Optical isomerism. Write one note that we will study separately in optical isomerism. But write note, a cumene with even number double bond, a cumene with even number of double bond can exhibit optical isomerism, can exhibit optical isomerism. Right, next, right, EZ nomenclature. EZ, capital E, capital Z. Nomenclature of alkene. Right. EZ nomenclature of alkene. Okay, listen. Now, so far we have studied cis trans nomenclature. Okay. What is cis? What is trans? Tell me, what is a cis? If identical groups are present on same side of the double bond, cis, and opposite side of the double bond is trans. Okay, fine. If alkyl contain highly substituted, it means like it is a it is B is there. Like it is C, it is D is there. Okay, here on double bond carbon, so no groups are identical. It is AB, it is CD, which is called highly substituted alkene. Like for example, double bonded carbon atom attached to, it is hydrogen, one side fluorine, here is chlorine, here is bromine. Tell me, can it exhibit cis trans isomerism? Huh? Can't it exhibit cis trans geometrical isomerism? What is the condition for geometrical isomerism? Carbon carbon double bond there, and each double bonded carbon attached to two different group, hydrogen fluorine, chlorine bromine. Two conditions satisfied. If the two conditions satisfied, it must exhibit geometrical isomerism, and moreover it exhibit geometrical isomerism. Can it exhibit ABCD, right? Not. It is also exhibit geometrical isomerism. Therefore, it exhibits geometrical isomerism. When it exhibits geometrical isomerism, then what is the cis and which is trans? Then how do you write cis trans? So in this case, cis trans nomenclature is not possible, which is called highly substituted alkene. Therefore, the cis and cis trans nomenclature not possible in case of highly substituted alkene. Therefore, the alternate nomenclature can be used, that is called EZ nomenclature. Right? This EZ nomenclature was developed by Kohn, Ingold and Prelog, which is called CIP, and they have given the rule called CIP rules. Kohn, Ingold, Prelog. This EZ nomenclature was developed by Kahn, Ingold and Prelog, and they have given the CIP rules, Kahn, Ingold, Prelog rules. Okay, it is a very simple, and there are 3-4 rules. Let's say first rule is, first rule, let us take carbon double bond having, like one is a hydrogen, methyl. Okay, let me take fluorine and chlorine. Okay, what is the first rule? First rule is identify the atoms or groups present on the double bonded carbon atom and give the priority based on the atomic number or atomic mass. That is the first rule. What is the first rule? Identify the atoms or groups present on each double bonded carbon atom and give the priority. So identify first fluorine, chlorine and hydrogen, methyl. Then give the priority to the each atom attached to the double bond carbon based on the atomic number or atomic mass. Okay, among fluorine, chlorine, whose atomic number is more? Chlorine. Therefore, give the first priority to chlorine. Chlorine is 1, fluorine is 2. Okay, it is 1, 2 separately. Next, identify the groups here, hydrogen and methyl. Methyl in the sense this carbon atom attached to carbon. Carbon atomic number is 6. Hydrogen atomic number is 1. Therefore, it is 1, it is 2. That is the first rule. Right? So, what is the first rule? Identify the groups and give the priority. It is based on either atomic number or atomic mass. That is, highest atomic number, first priority, or highest atomic mass, first priority. Okay. Then we have given the priority. Next, after giving priority, the identical priority groups are same side, which is called Z. 1, 1, same side, Z. If identical priority or same priority groups are opposite side, let us take chlorine here, this is methyl here, okay, hydrogen is here, here is fluorine. Now tell me, this is 1, it is 2, tell me, this is 1, it is 2. Then the same priority groups are opposite, which is called E. Therefore, here Z is called Zusammen. Zusammen. E called Entgegen. Entgegen. So therefore, you remember like that, E means opposite. Priority groups are opposite is E. This is first rule. Next, second rule. Second rule explains about again giving the priority. Suppose if the two double bonded, two atoms present on double bond carbon atoms are same, like for example methyl and it is a something ethyl. Here is let us take hydrogen, here is deuterium. Now first rule is identify the group and give the priority. Now while giving priority, we should see the double bonded carbon atom attached to which group? Carbon, here also carbon. Atomic number same, no? Carbon atomic number 6, it is also 6. If the two atom, the double bonded carbon atom attached to two same atoms or similar atom, then take the next atom for the priority. Then here, what is the next atom here? Hydrogen. Here next atom is carbon atom to attach to carbon. Therefore, it become 1. It become 2. Next, here hydrogen, deuterium. Then take the atomic number or atomic mass. Atomic number is same, HH, atomic number same. Atomic mass, deuterium is 2, hydrogen is 1. Therefore, this is 1, it is 2. Now tell me, similar identical groups are what? Same priority groups are same side. Therefore, it is a Z. This is second rule. That means, if the double bonded carbon atom attached to same atoms, then take the next atom for the priority. That is second rule. Third rule. If the double bonded carbon atoms attached to again doubly or triply bonded atoms, like for example C triple bond N, here is a C double bond OH. Let us take here is OH, here is a C double bond OH. Okay. Now, if the double bonded carbon atoms attached to double or triply bonded atoms, let us take C, attached to C double bond O. Now, if there is a C double bond O, C double bond OH like this, no? Now, here it should be taken similar, same atoms like that. For example, this can be written, it is H is same, the double bond, no, the double bond can be taken as 2 bonds. If molecule has doubly bonded atoms or triply bonded atoms, so you can consider, if it is a doubly bonded atom, two atoms, two such atoms are same, or if it is a triple bonded. Now tell me, now in case of here, let me finish this first. Okay, it is a C double bond O, means OO. Now this is what? It is same. Now give the priority. Which will come first? Carbon atom attached to oxygen. Then carbon attached to C double bond O. Which will get first? Obviously oxygen. You don't see the big group or small group. This carbon directly attached to oxygen, atomic number of oxygen is 8. Carbon directly attached to carbon, atomic number is 6. Therefore, this is 1, this is 2. Now come to here. It is a C triple bond N, right? If it is a C triple bond N, the C triple bond N can be taken as, which is equals to what? C, there are 3 such nitrogens like this. Next here, C double bond O, OH, which can be written, tell me, C, O, O and OH. Okay, now give the priority. So which has to get more priority? This carbon attached to carbon, carbon, same. This carbon attached to 3 such nitrogens. Here 3 oxygen, 1, 2, 3. So whose atomic number is more? Oxygen. Therefore, this get first priority, this is gets second priority. So 1, 1. Same priority group, same side, that is called, that is Z. So like that, you should write the EZ nomenclature. 1, 2, 3, only 3 rules. Right? Right on. EZ nomenclature, right? It is used for highly substituted alkene. It is used for highly substituted alkenes like, take these two. It is used for highly substituted alkenes like these two. Next, it is developed by Kohn, Ingold and Prelog. It is developed by Kohn, Ingold and Prelog. Kohn, Ingold and Prelog. Okay, next, right? CIP rules. Kohn, Ingold, Prelog rules. 1. CIP rules, or are in bracket, right? Sequence rule for EZ nomenclature. Sequence rules for EZ nomenclature. Sequence rule for E, Z nomenclature. 1. Identify the atoms or groups present on each double bonded carbon atom. Identify the atoms or groups present on each double bonded carbon atom and give the priority based on atomic number or atomic mass. Atomic number or atomic mass. That is atom with higher atomic mass, that is atom with higher atomic number, atomic mass. Atom with higher atomic number or atomic mass gets what? first priority, gets first priority. Next, second rule. If the double bonded carbon atom attached to two same atoms, then see the next atom attached to the double bonded carbon atom. See next atom attached to the double bonded carbon atom for priority, for the priority. Okay. Next, 3. If double bonded carbon atom attached with doubly or triply bonded atoms, it should be considered as 2 or 3 such atoms. Two or three such atoms. Okay, so take this C double bond O like this, C triple bond N like this. Next, fourth rule. If same priority groups present same side of the double bond, if the same priority groups present same side of the double bond, called Z isomer, Zusammen. Z is called Zusammen. Comma, same priority groups present in opposite side of double bond, same priority groups present opposite side of double bond, called E isomer Entgegen. Okay, so take 1, 2, 3 examples. Okay. So what is the nomenclature of Z? It is E. It is it is it is here there are two molecule. No, this is one, it is another one. First one is, it is 1 2 1 2. It's a carbon methyl carbon, but this carbon attached to different, no, 1, it is 2, therefore it is E. Next part is in next part, this is 1, it is 2. Here is, this is 1, it is 2. E. Next. Okay, will you do it later? Okay, do it later. Next, optical isomerism. Right, geometrical isomerism is completed. Next is optical isomerism. So this optical isomerism we have in second PUC, haloalkane, haloarine topic, but we will study here only. Right, listen. So what is optical isomerism? And let's see what basic concepts of optical isomerism. Tell me first, what is optical isomerism? The organic compound which are having same molecular formula but they differ in the spatial arrangement of atoms or group of atom around the asymmetric carbon, right? So if the, right, isn't it, the organic compound which are having same molecular formula but they differ in the spatial arrangement of atoms or group of atom around the asymmetric carbon. In case of geometrical isomerism, they differ in the spatial arrangement of atoms or group around the carbon-carbon double bond. If they differ in spatial arrangement of carbon-carbon double bond is geometrical isomers. If they differ in spatial arrangement of around the what? Asymmetric carbon is called optical isomers. Okay, then phenomena called optical isomerism. Then to understand optical isomerism, we need to understand some important concept of optical isomerism. Okay, one, what is plane polarized light? Listen first. What is the meaning of plane polarized light? Next is optical activity. Next, optically active compound. Next, optically inactive compound. Okay, next, what is dextrorotatory, what is levorotatory, what is racemic mixture, and what is enantiomer, and what is diastereomer, condition for enantiomer and diastereomer. So these things we are going to study in this topic. Okay, so let's study first. Okay, definition is, that's okay, optical isomerism. Next is plane polarized light. Tell me, what is a plane polarized light? To understand plane polarized light, we need to understand first what is the ordinary light. So when you see the ordinary light oscillate in all possible directions, yes or no? It oscillate all possible direction perpendicular to the direction of rotation, direction of propagation, no? This is a ordinary light. Ordinary light oscillate or vibrate in all possible direction which is perpendicular to the direction of propagation. Okay, so therefore, so the vibrations or oscillations are in all possible directions. That is in ordinary light. But in optical isomerism, we use plane polarized light. When this ordinary light is passed through the Nicol prism, okay, which is called a polarizer. Okay, it is a Nicol prism. It is one kind of prism which is made up of calcium carbonate, right? When this ordinary light is passed through the Nicol prism, then this Nicol prism adjusts the vibration of this light in one plane. Therefore, the light which comes out from the Nicol prism, which has the vibrations adjusted in only one plane, like this. Oscillations or vibrations adjusted one plane. This is called what? Plane polarized light. Right. In chemistry, we use only this plane polarized light. Then what is the importance of this plane polarized light? The important is when this plane polarized light is passed through any organic compound which is optically active. Let us take, it is a test tube which is having solution called optically active solution. When this PPL is passed through the optically active substance, organic substance, this solution may rotate PPL to either right side or it may rotate left side. Suppose it may rotate the PPL to right side. Now this is vibration in a one plane. It may become like this. Right side, no, take right side. Vibrations, no, it is just like this earlier. It become like this. Okay, or the vibration may become what? Left side. It is like this. Then if this organic compound rotate PPL to either right side or left side, then this organic compound is called optically active. Okay, if it is rotate right side, which is called clockwise direction, which is called dextrorotatory, this compound is called dextrorotatory. If it is rotate left side, it is called levorotatory. Then how do you measure this extent of rotation? How much rotated right side, how much rotated left side, which is measured by polarimeter. Okay, so this is the concept related to the optical activity. Okay, I repeat once again carefully. What is optical isomerism? organic compound which are having same molecular formula but they differ in the spatial arrangement of atoms or groups around the symmetric carbon. Okay, in other way, the organic compound which are having same molecular formula but they differ in rotation, that can also be said. They differ in the rotation of plane polarized light. One can rotate right side, other can rotate left side. Both are called what? Optically active isomers, and phenomena called optical isomerism. Then in optical isomerism, some important concept is first one, plane polarized light. What is a plane polarized light? To understand plane polarized light, we need to understand first what is ordinary light. So we know that ordinary light oscillate in all possible directions which is perpendicular to the propagation. So when you see the ordinary light, in ordinary light the vibrations or oscillation takes place all possible, one side, other side, no, all directions. That should be the perpendicular to the propagation. And when this ordinary light is passed through the Nicol prism, then this Nicol prism, when this is passed through Nicol prism, what happened? The vibrations are adjusted in only one plane. Therefore, now how do you define plane polarized light? The light whose vibrations occurs only in one plane. The light whose vibration takes place only one plane, which is called plane polarized light. Therefore, in organic chemistry we will use only plane polarized light whose vibration occurs only in one plane. Then what is the importance of this plane polarized light? The importance of this PPL is when this PPL is passed through the any organic compound which is optically active. If it is a optically active, if it is passed through the optically active organic compound, this optically active organic compound may rotate this PPL to either right side. This is a rotation right side, which is also called clockwise direction. Or this may organic compound, optically active organic compound, this optically active organic compound may rotate PPL to even left side also possible. It is called anti-clockwise direction. Then if this organic compound rotate PPL to right side or left side, then this organic compound is called optically active organic compound. But is it all organic compounds are optically active? No, may not be. Therefore, there are some organic compounds which do not interact with PPL. Some organic compounds do not rotate PPL to either left side or right side. It means they do not interact with the PPL. Such organic compounds are called optically inactive compounds. Okay. Then how do you measure the extent of rotation? The extent of rotation can be measured by polarimeter. There is a polarimeter which measures the how much rotation is occur. Right side, how many degrees right side, left side, how many degrees left side. And now this Nicol prism gives the PPL. Therefore, this Nicol prism is called, it is a polarizer. Therefore, the instrument which produce the PPL, which called polarizer. The instrument which measure the extent of rotation is called polarimeter. There was previous question. Polarimeter is measure extent of rotation. Polarizer produces PPL. Okay. So write down. First write optical isomerism. The organic compounds which are having same molecular formula. The organic compounds which are having same molecular formula, but they differ in direction of rotation of plane polarized light, but they differ in direction of rotation of plane polarized light, called direction of rotation of plane polarized light, called what? Called optical isomers, and this phenomenon is called optical isomerism. And this phenomenon is called optical isomerism. Next slide. Some basic concepts of optical isomerism. Some basic concepts of optical isomerism. Some basic concepts of optical isomerism. 1. Plane polarized light. Plane polarized light, right. Ordinary light oscillate in all possible directions. Ordinary light oscillate in all possible directions. Ordinary light oscillate in all possible directions perpendicular to the direction of propagation. Perpendicular to the direction of propagation. Propagation, comma, when it is passed through the Nicol prism. When it is passed through the Nicol prism, in bracket, polarizer. Nicol prism polarizer. When it is passed through the Nicol prism, the vibrations are adjusted in a single plane. The vibrations are adjusted in a single plane. Single plane. Which is called plane polarized light. The next point, right? The light whose vibrations occurs in a single plane. The light whose vibrations occurs in a single plane called plane polarized light. Called plane polarized light, comma, the device which produce PPL called, the device which produce PPL is called what? Polarizer. Called polarizer. Next, optical active substance. Optical active substance. Optical active substance. Right. The substance which can rotate. The substance which can rotate PPL. The substance which can rotate PPL either towards right side. The substance which can rotate PPL either towards right side or left side. Either towards right side or left side, called optically active substance. Called optically active substance. Next, optical activity. Optical activity. The property of the substance. The property of the substance to rotate the. The property of the substance to rotate the PPL. The property of the substance to rotate the PPL either towards right side or left side. Either towards right side or left side, called optical activity. Called optical activity. Next, optically inactive substance. Optically inactive substance. The substance which do not have interaction with PPL. The substance which do not have interaction with plane polarized light. PPL called optically inactive substance. Optically inactive substance. Next point, these compounds do not rotate PPL to either right side or left side. These compounds do not rotate the PPL, plane polarized light, either towards right side or left side. Okay.